Hello, everyone. Today I'm going to be talking about Kekulé spirals in twisted bilayer graphene. And I want to start by thanking all my collaborators who are listed down here. And with that, let me dive right in and give you a quick introduction to the topic of twisted bilayer graphene. So twisted bilayer graphene occurs when you take two monolayers of graphene, stack them on top of each other with a relative twist angle around about 1 degree, the so-called magic angle. And what happens is you get an emerging moiré pattern with a periodicity which is much larger than the graphene scale. And in experiments, what they can do is they can tune the density of electrons via gating in such a way that you change the number of electrons per moiré unit cell, which I'm going to denote by nu. And interesting correlated phases are observed as you tune this number of electrons per mole unit cell. In particular, at many integer fillings of the mole unit cells, you find insulating states shown in red in these resistivity plots. And in between these insulating phases, you observe these superconducting domes. And the interesting questions in this field are what the nature of these correlated insulators are and what the nature of the superconductivity is. And in this talk, I'm going to be discussing some progress we've made on understanding the nature of these correlated insulators at the integer fillings. So to solve this problem, we start off with the sort of standard model of twisted bilayer graphene, which is the so-called continuum model, which gives you a band structure that looks something like this, where you see these extremely flat bands. And most of the interesting physics is happening in these flat bands. And of course, correlation physics is going to be important when you have flat bands because the kinetic energy is small compared to the interaction energy. And in particular, these bands are 4-4 degenerate because you've got the Rayleigh and spin degrees of freedom. So really, you've got 8 flat bands. And so when you change the chemical potential from down here to up here, you're going from filling -4 to +4 per mole unit cell. And so we start with the standard model of twisted bilayers, but we add 3 experimentally relevant perturbations to it. So we add this non-local tunneling term, which breaks particle-hole symmetry. And in experiments, particle-hole symmetry does appear to be strongly broken. In addition, we add strain to the model. And again, in most experimental samples, strain is thought to be very important. And finally, we consider the effect of the HBN substrate on top of which these twisted bilayers are usually stacked. So we start off with the band structure given by this model with these 3 perturbations. And on top of that, we consider Coulomb interactions via the Hartree-Fock approximation. And before we set out to do this detailed Hartree-Fock calculation, we should maybe give a bit of thought to which state we expect to find. And really, twisted bilayer graphene is sort of at the intersection of 2 paradigms of strong correlations. On the one hand, we have the Hubbard model, which is thought to describe things like the cuprates. And in particular, these superconducting domes that are observed under doping twisted bilayer graphene are very reminiscent of the superconducting domes observed in the cuprates and indeed the Hubbard model. And from a theoretical point of view, you can construct localized Wannier orbitals and use those to build a Hubbard model description of twisted bilayer graphene. On the other hand, these extremely flat bands that you get are very reminiscent of Landau levels in the quantum Hall effect. And to drive this analogy further, these flat bands have Chern numbers, just as Landau levels do. And in experiments, the quantized anomalous Hall effect has indeed been observed. So since twisted bilayers lie at the intersection of these 2 different models, it's sensible to look for states that occur in both these limits. And indeed, one type of state that is quite ubiquitous in both Hubbard model physics and quantum Hall physics are translational symmetry breaking states. So in the Hubbard model, you get all sorts of charge density waves and spin density waves. In the quantum Hall effect, you can get strike phases and bubble phases when you've got partially filled Landau levels. So this motivated us to look for all sorts of translational symmetry breaking states in twisted bilayer graphene. And indeed, in our Hartree-Fock study, we found that one type of translational symmetry breaking is ubiquitous at all non-zero integer fillings, namely this incommensurate Kekulé spiral. So here I'm plotting the phase diagram for all integer fillings from -3 to +3. And on the x-axis, I'm plotting the applied strain. On the y-axis, the substrate potential coming from the HBN. And you can see that a moderately large strain of about 0.2% is enough to stabilize this IKS state for all non-zero integer fillings. And hence we propose that this IKS state is a robust candidate for the insulating state observed at non-zero integer fillings of the moiré bands. So all the other states listed here are already well known, and so I'm not going to discuss them any further, and I'm going to discuss the properties of this IKS state, which is new. So first of all, the order parameter for this IKS state looks like this. So we've got a coherent superposition of electrons in both valleys with a wave vector offset by some value q. And the intuition for why this order parameter is relevant can be gotten just by looking at the band structure. So here I'm plotting the band structure in valley K, and here the band structure in valley K primed. And let's think about half filling this this Brouwer zone with electrons. So what we're going to want to do is we're going to want to fill in the electrons in the low energy regions, of course, and avoid these high energy lobes. And furthermore, if we want to form a coherent superposition of electrons in both valleys and maximize this inter-valley coherence, the best way to do so is by shifting one valley relative to the other by this momentum q, such that this low energy lobe in the K point valley is on top of the high energy lobe in the K valley, okay? In such a way that in this region of the Brouwer zone, the electrons are all in valley K. In this region of the Brouwer zone, the electrons are all in, so in this region, they're all in valley K, in this region, they're all in valley K primed, and in the rest of the Brouwer zone, they can form an inter-valley coherent order parameter. So furthermore, let me discuss some of the physical properties that we found in our Hartree-Fock study of the state. So here I'm plotting the dispersion relation. So this is the energy of the IKS state relative to the lowest energy translationally symmetric state, which is zero energy here. And you can see that the lowest energy state has a wave vector q of about 1/3 of the reciprocal lattice vector down here. But in principle, there's nothing pinning this wave vector to any particular value. The dispersion is relatively smooth, and hence in general we end up with an incommensurate wave vector. Furthermore, if you use this dispersion to extract a stiffness and hence the BKT temperature, we find that it's about 7 Kelvin, which is consistent with the temperatures at which these insulating states are observed. So finally, let me discuss the real space picture of the state. So here I'm plotting the superlattice scale, and the shaded regions are these AA regions where the two monolayers are stacked in the AA fashion. And I've zoomed in into these 3 different regions, and I'm plotting on the graphene scale this bond order parameter CA dagger CB. Okay, so blue means that this order parameter is larger than 0, red means that it's less than 0. And you can see that in these 3 different regions, the bond order parameter has a different pattern as you go around one of these hexagons. In particular, here it's got this Kekulé pattern, okay, of alternating signs on alternating bonds. And this Kekulé pattern is shifting as you go from region 1, 2, and 3. And so this is really a way to visualize the IKS state in real space. Let me conclude at this point. So we did a detailed Hartree-Fock study of twisted bilayer graphene at all integer fillings. adding strain, substrate potential, and non-local tunneling to the model. And we find that the incommensurate Kekulé spiral is a robust candidate state for the insulators observed at non-zero integer filling of the Moore unit cell. Thank you for your attention.